right, to wrap up Unit 1, we're going to look at our last geometry application of the integral. We've found volumes, we've found lengths, we're now going to look at surface areas. We're back to our solids of revolution, and we're going to look for the surface area of the solid that's formed when we rotate a curve around an axis. So we'll start by considering our curve y equals f of x on some interval from a to b. Right? So we're starting here, stopping there, a and b. And f is just some non-negative function with continuous derivative. And we'll imagine revolving that curve around the x-axis to generate this surface of revolution. Notice that it's hollow. You can kind of see in the way they've drawn it. It's not a solid. It's just a surface this time. Our goal is to find the area of that surface. So what we're going to do is what we've typically done. We can't do the whole thing all at once. We don't have a formula for that. So instead we break it up into little pieces, right? You could imagine partitioning this into a whole bunch of little sections. And then if we just look at one of the little sections, imagine taking just this little piece, right? Almost a straight line if we were to take a small enough piece, but it's actually a little piece of arc length, right? We're going to revolve that little piece around the x-axis, which is going to create this band. You can see it kind of shaded in over here. Again, it's not solid, it's not a disk, it's just a band of surface area. And we'll start by trying to find the surface area of that little band, at which point we can then add up all of the little surface areas. So, surface area of this one little band. That band, as long as this is an almost straight piece, could be considered a cylinder, a hollow cylinder. And so all I'm going to do is look up the surface area of a cylinder, and that's just a geometry formula. It is 2 pi RH plus 2 pi r squared. Now keep in mind, when you look up that geometry formula, this is really the top and the bottom of the cylinder. That's the sides, the lateral surface area. And our band doesn't have any surface area on the top or the bottom. We just want the lateral surface area. So we'll get rid of this and keep just the lateral part. All right, so my surface area that I'm going to work with will have the formula just 2 pi RH. All right, like we've seen before, the radius of this band would be this distance right here, r, and for a function of f of x, this r is just going to be the y value. The height is going to be this little piece right here. This is h. And it's really that little piece of arc. Again, it's almost straight, but we know that actually this is part of a curve. So I'm going to think of it as a little piece of arc length that determines the height of my band. So I've got 2 pi y, and then for this piece of arc length, I'm just going to steal the function that we developed for arc length in the last section. It was the square root of 1 plus f prime of x squared dx. And that's just from the previous section. Right? If we integrated this, we would get the whole arc length. This is just one little tiny piece of arc length. Whoops. Dx, sorry. So that's going to actually give me my formula. 2 pi. The y value, notice I've got a mix of variables here. I got y here and x's in here. I can't have that. If this is going to be a dx integral, I need everything in terms of x. So let me replace the y with f of x. And then I've got this arc length piece, dx. Okay. Now, that's just the surface area of the small band. If I want the surface area of the entire surface, I would, of course, have to integrate this. So I'll pull out the 2 pi, and then I'll just integrate this function. Now, everything that we've done here has been very specific to rotating this around the x-axis. So this specifically works for rotating around the x-axis. If I want to rotate around the y-axis, let's take a quick look at the next page. Here we have a function x equals g of y, and we're rotating around the y-axis. I'm still going to use the surface area formula, 2 pi rh. But this time, notice this radius here is going to be x. And then my little piece of arc length here is going to have to be the arc length for an x equals g of y formula. So 1 plus g prime of y squared dy. And then I have a similar problem. I can't have an x in a y formula, so I'm going to replace the x with g of y here. And then if I integrate, I'll get the surface area for the entire thing. And I'm just going to refer us down to the bottom of the page because everything's written there. There's the full formula for going around the y-axis. So notice here, there's no choice in the matter. If you're rotating around the x-axis, you must have a function in the form y equals f of x. If you don't have that form, you'll have to solve to get that form. If you want to rotate around the y-axis, you must have the function in the form x equals g of y. Again, there may be times that we'll have to solve for one or the other variable to get the form that we need. By the way, in both of these cases, when I identified the radius, I was looking specifically at the radius with respect to the axis of rotation being either the x or the y. In these cases, we actually can do radii if we rotate around another axis, but I'm not going to ask you to do that. We'll stick with either an x-axis or a y-axis for the axis of rotation. So, those two formulas, what we're going to use. By the way, all of these formulas, just a reminder, are on your lists, right? We had the length formulas here on our lists, and here's the surface area ones. So keep those handy for looking them up, and it will serve you well. And let's do a couple of examples. In our first example, we're rotating around the x-axis. So I already know that when I rotate around the x-axis, I need to have the curve in the form y equals f of x. Fortunately, I do. So I'm in good shape on this one. I don't have to change anything. Okay. We're going to begin by just imagining what this would look like, and then we'll use our formula to actually find the surface area. Okay. Y equals the square root of x, going from x equals 0 to x equals 9. Square root of 9 would be 3. So it would look like that. And if you imagine rotating around the x-axis, this is going to be kind of like this. And we're going to want to find our surface area. All right, I'm going to start by writing down my surface area formula. And again, for going around the x-axis, we had, actually I forgot the 2 pi already, 2 pi times the integral from a to b of f of x square root 1 plus f prime of x squared dx. And kind of like arc length, there's not a whole lot of decision making. Mostly it's just a matter of paying attention and doing the integrals and derivatives correctly. So our function f of x here was y equals the square root of x. So I'll put that in for f of x. And then I also have the square root of 1 plus f prime, which would be 1/2 x to the negative 1/2 squared dx. And I guess I didn't put in the a and the b, but I will now. We were specifically told we were going from 0 to 9. So let me plug those values in. And let's see here. I've got the square root of x times the square root of 1 plus. Squaring that would give me 1/4 x to the minus first dx. Now again, there'll be lots of times where this integral will be complex enough that you won't be able to do it. This one isn't too bad. So let's work on this one a little bit by hand. Since these are both square roots, I can distribute that x through, and that'll become x plus 1/4, and x times x to the negative first is just x to the 0, or 1, so that 1/4 just stays a 1/4. If I were to let u equal x plus 1/4, then du is just going to be 1 dx. So I'm not going to need any little correction factors. I think I can probably do this one sort of mentally without even writing out the u. That would be like a u to the 1/2. So I'll end up getting that same thing to the 3/2. And then I'm supposed to divide by 3/2, but that's the same as multiplying by 2/3. And that goes from 0 to 9. Now, of course, if you're more comfortable actually writing out the u's, you can feel free to do so. But in this case, it wasn't too bad to just kind of mentally think it through. All right, so I've got 4 pi over 3 out here. Plugging in the 9, I would have 9 plus 1/4 to the 3/2 minus 4 pi over 3, and plugging in the 0, 0 plus 1/4 to the 3/2. And I don't think that's going to be anything that's going to come out particularly nicely. So if you want to just go ahead and plug that in the calculator. Let's see here. I've got about 117.319 when I get a decimal approximation for that. All right, we'll try just a couple more. In example 2, this one we're specifically supposed to rotate about the y-axis. So notice that as soon as we're trying to rotate around the y-axis, we must have the form x equals g of y. I actually don't have that yet. So let's get that first. This is just a straight line, so not that bad. If I solved this, let's see, we had, let me do it down here. Y is equal to negative 4/3 x plus 4. I'm just going to multiply everything by 3. 3y equals negative 4x plus 12. 4x is negative 3y plus 12. So y would be negative 3/4 x plus 3. All right. I just reversed my variables. X would be negative 3/4 y plus 3. There we go. All right. The original equation is very easy to graph, right? It's just a line with a y-intercept of 4 and a slope of 4/3. Like so. And we are doing this between x equals 0 and x equals 3. So we're doing this piece, rotating it around the y-axis. If you can visualize this, you probably know exactly what that is, right? That's going to be a cone when that revolves around the y-axis. So we're really finding the surface area of the cone that gets formed. Like so, when we rotate. When we solve this again, I'm just going to put it here so I can see it. This was x equals negative 3/4 y plus 3. And so now I'm going to grab my surface area formula. And again, I'm specifically using the one for going around the y-axis, this one right here. So we've got 2 pi, integral from c to d, of g of y times the square root of 1 plus g prime of y squared dy. Notice this is a y integral. So this had a y-intercept of 4 here. We're going from 0 to 4 on the y-axis. G of y, here's my function, x equals g of y. Times the square root of 1 plus, and g prime here would just be negative 3/4. We square that and integrate dy. Okay, this is actually just a constant, right? I could pull that constant out of my radical. That's 1 plus 9/16 or 25/16 under that radical. So I'm going to pull the square root of 25/16, which I'll simplify in my next step, right out of that radical. And then what's left in there is just that simple linear function, negative 3/4 y plus 3. Let's see, square root of 5/16, square root of that, square root of 25/16 is just 5/4. And this is going to be pretty straightforward, so let's go ahead and finish this one by hand as well. I would have 5 pi over 2, and this integral is going to be negative 3/4 times y squared over 2 plus 3y, evaluated from 0 to 4. So that would be negative 3/8 times 4 squared plus 3 times 4. When I plug in the 0, everything just goes to 0, so I'm subtracting 0 here. And you can just plug that all in your calculator if you want to, except for the pi. When I did, I ended up getting 15 pi. So a nice exact answer. All right, let's take a look at example 3. We'd like in this one the area of the surface obtained by rotating y is equal to the square root of 9 minus x squared over the interval as x goes from -1 to 1. And we want to rotate around the x-axis. So once again, just as a reminder, if we're going around the x-axis, we have to have the form y equals f of x. And in this case, we do. Y equals. So we're good. Don't have to solve it. All right. This is actually just the top half of a circle of radius 3. If you weren't sure about that, you could, of course, graph on a calculator or Desmos. And if you can imagine rotating that around the y-axis, what you're going to end up getting is actually a sphere. And we know the formula for the surface area of a sphere. So when it says check using geometry, we will do that after we find it using our surface area formula with calculus. So this time, since I'm going around the x-axis, I'm going to use this surface area formula. And let's see, we'd have 2 pi times the integral. Specifically, oh, you know what? I'm sorry. I think if we're going to check using geometry, we've got to do the same thing. Let's change this. It says -1 to 1, but I think that's probably a misprint. I probably should have said -3 to 3. Otherwise, we're not going to be able to do the geometry check. So from -3 to 3, my function, square root of 9 minus x squared, times the square root of 1 plus, and then the derivative of that function. 1/2, 9 minus x squared to the -1/2. Don't let me forget my chain rule here, times the -2x, all squared, dx. All right, let's see what we've really got under that big radical. These 2's will cancel. And so when I square, I'll get a positive x squared times the 9 minus x squared, and multiplying these exponents, that's going to become a -1. dx. And then I'm going to go ahead and I'm going to distribute this first radical into the big radical. So let's see, I'll have 9 minus x squared times 1 is 9 minus x squared, plus 9 minus x squared times 9 minus x squared to the negative first. When I add those exponents, I just get the 0 power, or 1, and all that's left there is the x squared. Well, this one's simplifying awfully nicely. Of course, the minus x squared and the plus x squared add up to 0. And under my radical, I've just got the square root of 9, or 3. So that's easy to integrate. Integral of 3 dx would be 3x, evaluated from -3 to 3. Plugging in the 3 would give me 9. Subtract plugging in the -3 would be -9. And I end up with 2 pi times 18, or 36 pi. All right, let's check this using geometry. The formula for the surface area of a sphere from geometry is 4 pi r squared. Since we happen to have a radius of 3 here, if I just plug that in, 9 times 4 does indeed give me 36 pi. So it looks like our answer definitely checks. Much easier to do using geometry, of course, but just kind of a nice way of verifying our surface integral or surface area formula. All right, one last example here for this section. We want to find the area of the surface obtained by rotating y is equal to the cubed root of x over the interval from 1 to 2, y equals 1 to y equals 2 specifically, and we're rotating about the y-axis. So we're going this way. Since I'm going around the y-axis, I must have my equation in the form x equals g of y. And I don't think I've got that this time. I don't have x equals yet, so let's get that first. If I cube both sides, x would equal y cubed. And that's the way I'll have to think about this one. All right, y equals the cube root of x. Just looks like this. And I could also label it as x equals y cubed. Notice it's just the inverse or the reflection of y equals x cubed. And we want to go from y equals 1 to y equals 2. So from here to here is what we're rotating. All right, this little section. And we'd be rotating it around the y-axis. Oh, try to draw that one, it's pretty small. So let's grab our surface area formula for this case. It is 2 pi integral from c to d of g of y square root 1 plus g prime of y squared dy. G of y is going to be the y cubed. And then under my radical, I'd have 1 plus. The derivative would be 3y squared. And I have to square that. dy. This is a y integral, so going from 1 to 2 on the y-axis is just fine. So I've got y cubed, square root of 1 plus 9y to the 4th, dy. All right, that's actually not a bad integral either. If I let u be what's under the radical, the derivative will be a y cubed rather, which I have here. We haven't done a lot of u substitutions lately, so let's go ahead and write this one out. Let's see, I'm going to let u be 1 plus 9y to the 4th. So du is going to be 36y cubed dy, and 1/36 du is equal to y cubed dy, which I have right here. So I'm going to have 2 pi times the integral of, that becomes square root u, and then the y cubed dy, I'll replace with 1/36 du. I'm actually going to divide out the 36 on the outside of the integral. Just put the du inside. I won't put my limits of integration right now because the 1 and the 2 are y values, not u values. So I have pi over 18, and that'll be times, it's u to the 1/2, so integral would be u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So I end up with pi over 27 times 1 plus 9y to the 4th to the 3/2. And now that I've got the y's back in, that goes from 1 to 2. Just going to pull out the pi 27ths. Plugging in the 2 first. 1 plus 9 times 2 to the 4th to the 3/2 power. Minus 1 plus 9 times 1 to the 4th to the 3/2 power. Let's see, I think I did that in the calculator. That's 145 to the 3/2. And that would be 10 to the 3/2. And that's about as good as you're going to get for an exact answer. It's not very pretty. If you plug all that in the calculator, the decimal approximation is about 199.48. All right, so that is the surface area of our surfaces of revolution. And that actually brings us to the end of 6.6, which is the end of Unit 1 as well.